there. Prime example, Morrison's own dark chocolate with hazelnut in it is the bomb.
Why Morrison's?
Because he works there.
Well, I
he
do
has
work
easy
there.
access.
Well, do you know what's even funnier is the fact that I wouldn't even have had it if it wasn't for my colleague membership there. So obviously, because not only am I a member to the Morrison's colleague thing, Morrison's joint thing, but I'm also a colleague. You get bonuses, and one of the bonuses is when it's your birthday. If you scan or buy an item near or around your birthday, the Catalina vouchers print out something, and it printed out 2 vouchers for myself. One was like £2 off anything over £10, and the other one was a free chocolate bar of this range. So it told me that the exact weight, and it was a variety of them. So I went over to it and redeemed it at the same time. I think it was like 26, maybe 25. So it was a couple of years ago. Went over and I saw the lineup, and they had nothing that jumped out at me other than hazelnut. I love hazelnut and chocolate, but it was a dark one, and I thought I've never tried dark chocolate, so I gave it a whirl, and it was incredible. That's when I started with dark chocolate.
Switching functions.
Meanwhile, in the real world.
Okay, blah 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 blah. Switching theory, blah blah.
I'm putting this in the exam.
Quality.
This is so worth 9 grand.
Quality information.
Actually,
Oh, I just feel like I could throw them in.
There it is. Switching function.
You might have to eventually one day apply it. To Are you done with math up this year? This is it.
No.
Are you off into HR?
so and n-ary switching function or Boolean function, if you like. Okay, is f, which takes n zeros and ones and gives you a 0 or 1 for each n tuple of zeros and ones. Okay.
Is that an array
What do you mean an array?
and an array?
An array, yeah, an array.
What the hell's an array?
An array.
An n-ary switching function, as in it takes an n number of inputs and switches them.
Oh, I've never seen that one.
So it's not a word to say, as more of a mathematical suffix applied to n.
Right.
Do you know what binary is?
Yes.
Ternary.
No, I've not heard that one.
So what is a binary thing?
Well, binary is zeros and ones.
Something else takes about
2 options.
What's unary?
human one.
Ah.
What's ternary?
So 3, I take it, yeah.
What's quaternary?
I guess 4.
Probably. So n-ary is,
By how many
letters?
of that?
yes, so
Right.
it takes n. Okay, for example,
Thank you.
this, right? Do you know that?
Is it out?
It's either a hat. I've missed a bit, so it's just above here. Oh, it's a. No, it's not. It's a bullet module. It's R
And.
And
I was getting all the way around.
Okay, so 0 and 1 is 0. And so on, you know that. Another example. Okay, so basically logical connectives are binary switching functions and binary Boolean functions. They do take, well, no, they take the, not when working on propositions and stuff like that, when we're working on the truth values, they do this, okay? And then that's Boolean functions, binary. Unary Boolean functions are, well, there's only the negation really, and the identity. because it only takes a 0 and 1, and then there are constants. So there are 4. Okay. Boolean. How many Boolean there are? How many Boolean functions? Oh, sorry, binary Boolean functions are there? 2. You reckon?
By functions, you mean the listings?
No, by function I mean a function. Yes, but what I'm looking at is binary Boolean functions. Okay, so this AND is a binary Boolean function. It takes 2 binary digits, so two things that are either 0 or 1 each, and it gives you a 0 or a 1. Like if you take 0 and 1, it gives you 0. Okay. If you do 0 and 0, it's 0. If you do 1 and 0, it's 0. If you do 1 and 1, it's 1. Okay, so that's a Boolean function. The implication is another one. So 0 implies 1 is 1. And 0 implies 0 is 1. And 1 implies 0 is 0. And 1 implies 1 is 1. So it's like this. Okay, so
Yeah, I was just about to say.
now you see how useful it is.
No.
It's everywhere.
Yeah.
Especially if you want to construct a binary electric circuit, something digital. Anything, yeah. Digital circuits, there you've got things like that all the time. So there are plenty. In some sense, there are 16. No. Yeah, I think so. Hang on. Yeah, 16. Why are there 16 of those? Sorry?
There are 2 sets of operations of binary Boolean. So we're gonna.
No, I don't think.
Oh.
What's the answer?
What's the question?
I have no idea.
So the answer is 16. That's my question.
I just had 2 hours of Lido. My brain doesn't work anymore.
You can't always take Lido as an excuse. Everybody does it, I know. Okay, there are 16 different binary, so arity2 switching functions. Why? Well, because there are 4 different inputs. Right? So written them in a slightly stupid order. 2 zeros, 2 ones, 0 and 1, 1 and 0. 4 different inputs. And for each of them, you have a 0 or a 1. So when you list the inputs like this, how many things can you put there? Different sequences of 0s and 1s? That's 16, because here it's a 0, 1, here it's a 0, 1. So that's 16 options. Or if you want to count them from 0, 1, 2 binary digits. And all 1s is 15. So you go all from 0 to 15 as a binary number. Okay?
It does take me a while to get through this.
No, this should take half a minute because this is so fundamental and easy that, well, easy, fundamental that everybody should remember, well, know this, like really, like from year 1, no, year 0, I don't know. Okay, so it's my fault.
Yeah.
Take away the operation in the middle and just think about it as the 2 inputs and an output. There are 16 combinations of 2 inputs. 1
Oh
output.
no, I get that.
Yeah.
because again, it's just like there's 8 operators there, and there's 2 possible answers, 8 times 2. You can think of it that way. But that I don't get is the fact that with binary operations in like Jones, is that 0 and 1 is supposed to be 1, 0 and 0 is supposed to be 0, and 1 and 1 is supposed to be 0.
That's specifically one. That's a different operation.
That's what's wired in there, though. That's the problem.
That's bitwise addition. And bitwise.
There's 16 different ones.
It's
So you
just
can
like I say,
have-
it's just that hard wiring of that from last year.
You can have 16 different logical connectives. You have the and, you have the implication, you have the or. They're the most commonly known binary logical connectives. So this one works. This is 0. This is 1. This is 1. This is 1.
The one you're thinking of is the other one.
Because that's or, and
And
that's
that's
and.
your exclusive or is what you're thinking of. Where it's only 1 if it's 0 and 1.
Right.
2 ones together is 0.
So is that an and operation, that one?
That's all.
Well, that one's all. That one's and. Oh, yeah, and. Yeah,
So-
yeah. Looks like an end, doesn't it? Right, yeah.
So one of the so this is so when you do you don't really, if you were like 30 years older, then in your age you would be studying things that look like this in electric circuits, because digitization is picking up and everything is so people start building gates and transistors. That was about, digitization in the 50s, 60s, probably, 70s maybe. And what happens is you've got let's get electricity coming in or not coming in. Okay, so if it's not coming in, it's like a 0. If it's coming in, it's like a 1. And then depending on these 2 inputs, this is output into. So you can build a gate like this for any of these binary functions. Okay? So depending on what the input says on, so you've got the inputs A and B, and there is some output out. Okay. And this out is a function of 2 0 1s, so 2 binary inputs. And it's the same thing. So it's motivated really by electric switches, kind of thing, electric gates. It gives a very strong connection between computing and logic, because it was logicians who invented the first computers, like Alan Turing. And before. But these people were working with the first computers, and at the heart of a computer are circuits that can do this kind of thing. Okay? So simple binary functions, because every ternary one you can build from linking several binary ones and so on. And in fact, there is one which is, well, there are actually a couple of 2. One from which you can build anything you want, and that's the NAND, which is not the negation of and. So I don't know what it's called. Let's call it like this: negation of an and. So the end would be 0. So this is 1. The and would be 0. So this is 1. This is 1, and the only case when this is 0 is this. And that's a very useful gadget because, for example, it can do negation. Because when you have x and you want not x, then what you do is x and x. So if x is 0, you get a 1. If x is 1, you get a 0. So if you're trying to negate something that's coming on a wire, you just split it, put the NAND there, and so if x is coming on the wire, then here you have the negation of x. Okay. So from this, if you have this gate, you can build any gate whatsoever. There's only one that's necessary. But maybe you want some others as well. Now the question is, how many are there in all? And of course, we've just said that there are 16 of them. But we're talking about counting orbits, aren't we? So, so we want some of them to be equivalent, and what we want to be equivalent really is when you switch the inputs. Because you can always, when you're just wiring them, you can always switch the inputs and wire them in the opposite way. So switch A and B. And you don't need one gate that works for A and B and another one that works for A. That makes sense. For example, so these three are symmetric. It doesn't matter whether you switch these two or not. Okay? 0 and 1 is the same as 1 and 0. Same for all. But this one is not symmetric because 0 arrow 1 and 1 arrow 0 give you two different values. So there's another one where you swap these two. Okay? But you don't need to make them. If you're making them with an electric arts maker, then you don't need to make them both because the people using them can just switch the inputs and get the same thing. The question is, how many do you have to make if you want all possible binary functions, or you're allowed to switch the inputs any way you want? The question's not clear. Zero.
We'll chair up in about 27 minutes.
Okay. I hope it's still the ODEs I thought.
It's a bit of that, I think. Yeah.
Okay. So when you look at the table here, page 234, which I'm not going to reproduce on the paper, you can see that it actually says on the previous page. Okay. What does it say on the previous page? F2 and F4 are the same. They just you just switch the two inputs. So you switch the two columns here. This one becomes that one, and that one becomes that one. What this one says for 0, 0 is the same as what this one says for 0. So what this one says for 0, 1, same as what this one says for 1, 0. And what this one says for 1, 1 is the same as what this one says for 1, 1. Okay? So these two are the same. 3 and 5 are supposedly the same.
12.
Yeah.
11 and 13.
Yeah. Well, if not, looks like it's true. So you see that. So you see they have a partner exactly when these two values are different. And when these two values are different, you get the other function where these two values are reversed. Different, reversed. Well, here, if you reverse them, you get the same. Here, if you reverse them, you get the same. So what you see is group action. So you have S2, which is the group of individual elements, acting on a set of all these functions. So the identity leaves everybody in place, and the transposition, being the other element is 2, maps a function to the function where these two are. Because that's the only thing that changes. Okay. This is quite easy because we can actually come them by hand. Again, this is helpful. However, we wanted to do it using the orbit counting lemma. We have an action. So this is S2 acting on, and I call it X tilde again. And X tilde is the set of all binary switching functions. And act by, so the action is, to get a permutation and a Boolean function, this is a function which, if you get some inputs, so the inputs were A, B. I said AB, but I don't want to say AB because I want to say A1, A2. So this is a function which, if it gets two binary inputs, what it outputs is what F would have said for when I switch. Oh no, rubbish again. Excuse me. A, the index is sigma 1, and A, the index is sigma 2. That's the action. I'm going to put it all together correctly. Okay, so the sigma is S2. So it's permutations of 1 and 2. And there are only two permutations of 1 and 2. One is that maps 1 to 1 and 2 to 2, and the other one maps 1 to 2 and 2 to 1. Okay. Normally, F gets A1 and A2, and both A1 and A2 are 0 or 1. So if you get a function, there are 16 such functions in all. Get a function like this. What the permutation does to it is it switches, well, if it's the identity, it does nothing to it. And if it's the transposition, then it switches the input. So sigma 1 will be 2, and sigma 2 will be 1. So for the transposition, you will get F, A2, A1. Okay?
Yeah.
Okay. It's harder to explain. So S2 contains only two permutations. Well, the identity and the transposition. How many fixed points? Well, this one fixes everything, and we said there were 16, and they're listed in the table, so it has 16 fixed points. Now this one, what's it do? That's the one. That's the one that so when you do this, and do AB again, this will be FBA. Okay. Oops, no, it's not okay. So if this F is to be the same function as the switch function, then it will necessarily be the case that where these two differ, when you swap them, you get the same value. Okay, so 1, 2 fixes F exactly when FAB equals FBA or AB. Okay. So now going back to the example, I'll make this clear. In fact, what I've drawn here is the action in a way. Okay? So this is what the transposition does to the functions. This one is moved here. This one is moved. This one is moved to 13, 13 moved to 11. And all the ones that don't have a state fix. So these are fixed points. Those are fixed points. Because these three values are in okay. That's quite. So how many did we count such functions? Well, by hand you can count it. So 1, 2, 3, 4, 5, 6, 7, 8. 8 are not like that, so 8 are like that. Well, you can also say that there must be 8 because you have freedom how to choose this value in that function. You have absolute freedom how to choose this value in that function. And then you have the freedom how to choose the value that has to be common for these two inputs. So you can do 8 different functions that are these two. Zero or 1 here, 0 or 1 here, same value there, 0 or 1 here. 3 times you can choose.
It's very difficult.
Wow.
Okay, so this one has 8 fixed points. Average is 16 plus 8 divided by 2, which is 12. To verify, they're actually 12. Okay.
What?
Just worked out.
What is?
So that's the orbit counting, am I right?
It's
The
not
average number of
constant,
fixed
it's
points.
It's 12 orbits.
Yeah. And you can see all the orbit here. One orbit, second orbit, third orbit, That's how it works. Okay, one thing which is not in the book, which I invented this morning when I was thinking about it.
This is always a dangerous.
Definitely. Same way that Killian says don't ever do, what was it, maths in front of people.
No, computer thing.
Yeah.
John said all the time. But I also remember that time. I don't remember at the time that this guy, Brian Cox, pretended to disprove Einstein on the lectures and realised he made a really basic math error somewhere in one of his first years picked him up apparently. So you don't invent things, though. Show people.
Okay, this one I actually know. So this is a square. Okay, and now I want you to tell me how many ways there are to color its vertices black and white.
For your pancake. No, it's 16. Yeah. Oh, I actually remembered something. Good night.
But that's an interesting coincidence. There were 16 binary Boolean functions.
Here we go.
So this vertex is 0, 0. This vertex is 0, 1, 1, 1, 1, 0.
Oh, because it works the same as how to say there is algorithms that work on blank square.
Okay. Now the group acting on the square, however, is not the one that rotates it or whatever. The group only. So we have S2 acting on it. So it's a group which acts by using the coordinates of. Sorry, for using the entries in the coordinates. Okay. This vertex is coordinate 0, 0. Vertex is coordinate. I think I should have done it 0, 1, and so on. So think of them as coordinates. What the group does is it can use the coordinates. So there are two permutations of two coordinates. Right? The identity is nothing, and the other one is just the the coordinates. So this vertex always takes place. This vertex always takes place. And then there is one information which swaps these two vertices. Okay? And so under this action, we're trying to find how many different colorings there are. Okay, so now black and white is the same as black, 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 white, because we can get one from the other by using our action. Okay. Before that, what we were using as transformations was rotations and reflections. Now we're only using permutations of coordinates. And we'll get the same result, obviously. Because the colorings that are fixed by this reflection, if you want, then it's blocked, are exactly the ones where this and that vertex get the same color. So you've got 8 different colorings that are fixed by the position. So you can pick black or white here, black or white here, and black or white for the to which I share. So 8 possible that fixed. And this one is not fixed. Okay. Same result of this. Again, one permutation fixes 16 colorings, one permutation fixes 8 colorings. So on average, they take 1. Now, it's almost an info telling you that they are related, right? Because you can think of the color as the input of that output. So here I would, this is my new notation for a function which says 0 for 0, 0, 0 for 0, 1, 0 for 1, and 1 for 0. Okay? So binary switching function and two coloring of a square are the same thing. How much time is left? Oh, really?
Yes.
Yeah, I didn't really want to do anything else than switching functions, so it doesn't really matter, but I still wanted to do ternary switching functions.
Benzene, man.
Why should there be a circle?
Okay, so this is the case where n is 3. So we're looking at functions that take 3 binary digits, 3 zeros or 1s, and give you a 0 or a 1. Okay, how many such functions? Without any symmetries?
Two.
2 different functions.
32.
32.
55. Just guess the moving about.
No, well, there was this table, which for every 4 tuple of zeros and ones, sorry, every pair of zeros and ones, of which there are 4 different ones. You see the table? So if the input, if there was another column, zeros and ones as input, how many different Fs would you get? That's the question.
I'm gonna go with 32.
What, 32?
Just double up the amount. There was one choice
That's
before.
why I think I'm wrong.
If there was one choice it would be 4, like you said at the very beginning of the lecture. Now that we've got 2 inputs, it's now 8. So I would have thought 3 would double it to 16. 16 twice.
So you've got 8 different inputs. Is that what you said?
There's 8 there on the outputs enlisted. 0 0 0 0 0 0 0 0 and 0 0 0 0 1 1 1 1. So I would have thought that would just double up in size. It's the same way of having how many outputs you can have of a coin flip. And that's 8. You can have heads, 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 tails.
That's quite right, yes.
Yeah.
So every one of those 8 things, for each of those 8 different outcomes, you get a 0 or a 1.
Mm.
And how many ways can you do that? That's the question. So it's much more like another layer of depth.
If you got NTR or NCR,
What is it?
So for each, so if you wanted to describe such a function, you'd take all the 8 different triples of zeros and ones, and for each of them you'd have to say whether that's a 0 or a 1. But here, you take all the 4 different pairs of zeros and ones, and for each of them you say whether the value is 0 or 1.
So-
each of these,
So meaning if the input was 0, 0, 0,
Hmm.
and the actual function was 0, then that's 0 only. So then if it was 0, 0, 1, that'd be that would be 0?
no, that's up to you. But in how many ways can you explain it?
That's what I want to do.
I need to get you one to do to think about.
It's two ways of
That's an interesting one.
That's 9.
That's some power of
That's
3.
9 cubed.
Is it 3 to the 8? 3 to the 6? Yeah, it is 3, yes. Better than 8. So what did you get?
That'd be 18. That's not right. That's not right. Well, that's also taken 2. Well, that's also
Is
taken 2. Well, that's taken 2.
8
I think you're already counting some sort of how many orbits or something. In your-
There's 3 inputs. No, no,
No,
it's
no,
0,
no, no.
1.
It's 3 0 1s.
So
Aha, so
there
that's
are 3 actual inputs for 1 output, but they can only be 0 or 1 still.
So now you're looking at a gate which would have 3 things coming in. Each of them is a 0 or a 1, and 1 0 or 1 coming out.
0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0. 8.
Yeah, that's 8.
8 input.
Yeah.
Mm-hmm.
And for each of the inputs, you're saying 0. The function is saying 0 or 1.
So for the first one, it's all 0, the A, B, C, like, or I was doing 0, 0, 0. But the function is 0, then that would only come out 0.
But the function can be anything.
Function can be anything.
No, 1 second.
No, I'm halfway there, and I'm still trying to do it in my head.
Okay,
I'll tell you what.
here we have 16 functions because we have 16 functions. So you list 4 different possible inputs.
Oh my god, it's just falling. It's just,
Go on.
it's just,
4 different inputs, and for each of them you get a 0 or a 1. So you've got 2 times 2 times 2 times 2 different functions.
16.
Now we've got 8 different inputs. We get 2 times 2 times 2 times 2 times 2 times 2 times. 2 to the 8.
2 to the power of 8.
Which is 256.
Which was right there.
oh, it's on the page, yeah.
Mhm.
Yep, that's the right one.
That
That would be 16 again, which is what I got the first time. But this time I did it in binary. Ooh.
Okay, so there are 256. Now you start permuting the inputs using the group S3. The question is how many essentially different ones. So if you were implementing that as a circuit, so you've got 0, 1 input in there, 0, 1 input in here, 0, 1 input in here, and something goes out. Now, how many different parts like that would you have to produce so that you capture everything? Meaning that the user who buys it can just, if they want, they can just switch the inputs in the wire.
And now there's 6 different ways of putting them.
There's 6 different ways of permuting them. It takes a bit of work, but it's not too much work. I've done it here on this much room on the paper. Okay, so it's not so much work.
Put that on the other.
I got 80, so can you verify that it's 80?
It's 80.
And we can check that on Friday.
Trying to work out how many outputs you would have from A, B, and C being commuted 6 times.
Right.
Yeah, but you
Zero
have,
or 1, so you've got 6. You've got 3 factorial on 2 different options.
You've got the two are standard, but they're just all on or one.
Yeah.
yeah, so they have no partner.
But then they can be 0 or 1. Because either or
Oh, so that's
off.
4.
Like I say,
yeah,
if
yeah,
A,
yeah.
B, and C were all off,
Yeah.
that would all be zeros. But then A, B, and C are all on, and then they were all zeros. But then the exact flip, so then you say 4.
No, I think I'm not entirely sure you're thinking around the
No, I'm thinking
right lines. So what it is you've got all these possible inputs. There are 8 of them.
It's only been all taken.
I've done them in order. Okay. This is binary 0, 1, 2, 3, 4, 5, 6, 7 binary. Okay. Now the function for each of them is going to say a 0 or a 1. So the first one, which was called f0 in the table above, will give 0 no matter what you put into it. I don't know why anybody would want a part like that in their circuit, but it's one possible function, switching function. Okay. Then you get another switching function, which they called f1, and they did them in order like this one only switches on if you put all ones. Okay. Then they did one, which was called f2, which, whoops, I've lost my lines. One, which only switches on if the third input is off and the first 2 are on. Now, of course, this one has a partner, which is one. Well, there are a couple there. So, for example, there will be a partner if you permute these 2. So, if you get a function which only switches on when you get 1, 0, 1. So, that's called F4.
Oh, because it's completely different.
You look at the album.
Right.
I think that's the problem.
Yeah.
So these 2, F2 and F4, will be in the same orbit because the permutation that switches the second and the third input sends one to the other. Okay, so there, yeah, and on 1, this one, and you get the black one. So if you have a circuit, if you have a gate that does this, you can get a gate that does this by wiring the second and third input here the one way out. So what you're counting is how many different gates you need in order to be able to get all these functions just by switching the wires. That's what we've been doing all day today. Okay, I'll let you think about it, and it's a good, I think, it's a good invitation to the tutorial. You should check that and get it done now. The one way of thinking about it is you take the group S3. What is essential for counting the fixed points is the cycle structure. So there are not so many different cases. There's one that's the identity. There are 3 cycles and there are 2 and 1 cycles. And then another way of thinking about it is black and white colorings of the cube, vertices of the cube.
We're going to get a cube in 3D space.
Yeah, because n is 3.
Yeah.
If n was 4, then it would be a cube in the 4D space. Okay, that's it from me now.
Visualizing in 3D space.